So today I want to talk to you about line charge distribution. So whenever you have a charge distribution, you know that finding field becomes a little bit of a pain because you need to integrate, right? If you had point charges, it was quite simple. But if you had a line charge distribution, you need to integrate. And particularly, we do have nice formulas for infinite line charges. But if you had like a finite line charge, it's very messy. But it is actually nice, therefore, if, for example, I had a nice formula for a finite line charge, and a formula that you could remember well, obviously makes things quite easy. I have been looking for one like this and just recently managed to find one. So I want to share with you that because it's a very thrilling thing for me too. So you will find that it's a neat formula that it's not something that I would have expected, but it turns out to be true. Now, if you look at this is not symmetric. First you have to understand that this is a finite charge, line charge, uniform charge of charge density lambda. And at this point, can you say that the field will point like that? No, right? Obviously, it won't point like that. Why? Because if I draw, let us say, a perpendicular, now you see that first of all, the charge on this side is much smaller than the charge on that side. So the overall field like that is going to be pointing that way, one. And this guy's field is probably going to point like that. You expect that the net field is not going to be like this. It is going to be like that. If it was a more symmetric question, right in the middle, then you expect that all this element and corresponding element on that side, the components, horizontal components should cancel. You can't say that here at all. In fact, it won't cancel, right? Now, suppose I had a different situation. Let us say I had a situation where I had an arc. Let us say an arc like this. Now this arc, I have consciously not drawn it like this, I have drawn it like that. Now suppose I want to look at its center, somewhere there, okay, I want the field. What do you think will be the direction of the electric field? This is also lambda. What do you think will be the direction of the electric field? So what do you think? So if you think a little about it, you can say, well, this does not look symmetric just because I have drawn it in a tilted way, but it is symmetric. It is not that it is not symmetric. It is not symmetric about an axis like that, but if I had took an axis like this, it is quite symmetric, right? So if I draw this, then you could take a element here and you take a corresponding element there. This element is going to produce a field like this, and this element will produce a field in this direction. And you expect that these two will cancel, and so the net field because of these two will point in this direction, right? So I can then conclude that for this thing, the field is along the angle bisector. So if the angle was theta, this would be theta by 2, and this field is along the angle bisector. So I can say that the field actually right in the middle, you can do that. Now, but if you look at this, do you think it is obvious that if I drew two lines, let us say these two lines, now this angle is theta, I can always draw an angle bisector. Now, do you think this will be the angle bisector? Clearly no, right? This angle is more than that angle. Maybe this was, let us say, some 40 degrees, and that was 60 degrees. So total is about 100 degrees. So the angle bisector will make an angle of 50 degrees. So it won't be like this, it will probably be like that. So in fact, you know that the angle bisector will be like this, right? Now, do you think it is obvious that the field of this thing is going to point like that? See, here it seemed reasonably obvious that the field was pointing right in the middle. Is it obvious that it points like that? No, right? It doesn't look obvious. But it turns out that it is. The field is pointing like that. Field is along the angle bisector. First of all, that's easy to remember, and it's also worthwhile. It's surprising. Why is it not so obvious? Because here there is a symmetry. Here there is no symmetry. But there is much more. Okay. So what I just discovered, and that's why I'm telling you that I'm quite thrilled about it, is that if I replace this line by an arc. Okay. Now I'm going to construct an arc with this as the radius. Okay, and so let us say I have an arc which goes from here all the way till there. So this is the arc. Okay. Now, this angle bisector would be the direction of the field for this arc. Okay, let's think a little bit more. I have not drawn it properly, so let me correct for it a bit. So I should take the angle bisector. So if I took this whole angle, probably the angle bisector looks like that. And this is the direction of the field. Now, is it clear that for this arc, that would be the direction of the field? Yes, because that's obvious from there, right? Okay. Now, it turns out that the answer for this arc is the same as the answer for this line. I'll prove that. But right now, think about how surprising the fact is. This and this, first of all, the lengths are not the same. If I thought of a new arc like this with lambda, you can clearly see that this one is not going to have the same charge that this one has. In fact, just by looking at this diagram, it looks like this one has much more charge than that one. But this whole thing's field and this thing's field are exactly the same. And I'll tell you the field. The electric field is along the angle bisector for a line or for an arc, and they are the same. And the answer, if for example I thought of this, so let us take the radius of this thing as r. So that means this perpendicular that I'm dropping has length r. This is r. I don't even care about this length. I only care about this r. And then this angle, the total angle between from this end to that end, let's call that theta. Then the electric field, it turns out, is a very nice and simple formula. Lambda by 2 pi epsilon naught. So remember 1 by 4 pi epsilon naught, this is 1 by 2 pi epsilon naught r. Now this formula may look very simple, except that this is not the answer. This electric field, which is like that, is this into sine of theta by 2. Okay, so this is the electric field of a line or of an arc. Actually, it turns out for this arc, the answer is lambda by 2 pi epsilon naught r into sine of theta by 2, and it is exactly along the angle bisector. But the fact that it is along the angle bisector is easy. In this case, it's quite easy. The fact that it is also along the angle bisector here is not so obvious. So I want to mention the fact that you should keep that in mind. And this is such a nice formula that it's actually worthwhile. Why is it worthwhile? I will now show you how you can use this in 2-3 different places. But then we can also see, then we will finally prove it, but you can also see that this is a reasonably easy formula to remember. For an infinite line charge, you will remember the formula lambda by 2 pi epsilon naught r without the sine theta by 2. I'll show you that with this sine theta by 2, it will actually turn out that it is the same answer. So let us first use this a little bit, and then we will come to proving it. Now let us take something like this, which you already probably know. I have an infinite line charge. Okay. Now I want the field here. Now this distance is r. What I'm going to do is to say, if I had if for example, if this was not an infinite line charge, suppose the line charge stopped somewhere there, then you would have drawn it like this. So that means you would have drawn this line, and then the arc would have basically extended till there. Now suppose this line extended a little further. Then what do? Your line would extend all the way there, so the arc would extend a little bit more. Can you see that it's extending a lot in the beginning, and it starts to become smaller and smaller? Now when this becomes infinity, this will increase slowly. Where do you think it is going to end if this was going to infinity? Suppose this kept going forever. What is going to happen? This guy will keep going. You know that this line will basically become parallel. And if it becomes parallel, so what kind of arc am I going to get? I am going to get a quarter circle. Okay, so this part of the line has basically become a quarter circle, because this is the line extension. So this is the line that's going to meet that line at infinity. Now what about in this direction? So similarly, if I, for example, were to stop here, then I would have had an arc that went up to this place. So let me actually show you. So for example, if it was still here, the arc would have basically extended till here. And if this line went further, the arc would have extended till there. And if this line goes forever, the arc would have extended all the way till here. And what I'm claiming, this particular claim, is what does it say? It says the answer for the infinite line here, the electric field here, and mind you, this is only for the electric field. You can't say that the total charge here is equal to total charge there. You can't say that the potential due to this here is the same as the potential due to that line here. That is not true. I'm only saying for the field. Okay, so the field of this line, infinite line, is the same as the field of this semicircle, right? But you already know the answer for the field of the semicircle, which we are again going to derive, but this is the formula that I have told you. Now, what is the angle made by the semicircle? 180 degrees. So, what is theta? 180 degrees. So, what is theta by 2? 90 degrees. So, what is sine of 90? 1. And so, therefore, the electric field is lambda by 2 pi epsilon naught r. This is the formula you probably already know. Okay. Now, what is very interesting is what happens to a half infinite line. That is, it starts here, the line starts here and goes off to infinity. Now, there is a good interesting formula for it, but this will tell you why that formula works the way it works. So, let us look at that. Okay, so now we have done this for an infinite line, right? Now, let us take a semi-infinite line. That is, I want the field here. The line starts at this point and goes off to infinity there. I would like the field here. Now, you know that obviously you don't expect that the field is going to look like this. It's going to have a component in this direction and a component in that direction. In fact, you can expect that the field is going to look like that. This tells you it must be the angle bisector. So, what does that mean? Instead of using this arc, suppose I wanted to just use the fact it was angle bisector. What is this arc? Where does this thing meet? Well, if it stopped here, this is where it's going to meet. That would be the angle. Whereas this is now going off to infinity. So, this angle is going to become 90. And the angle bisector would be 45 degrees. So, you expect that the field is going to be at this angle. What angle? 45 degrees to the x-axis. Now, that tells you something very interesting. It tells you whatever this field is, its component in this direction is E cos 45 and its component in this direction will be E sin 45, but sin 45 is cos 45. So, therefore, this component must be equal to that component. Okay. Now, if you know that, I don't even need to know this formula, but I'm going to use it. Because if I already know the answer for an infinite line charge is lambda by 2 pi epsilon naught r, the component in this direction will be the same for this guy and for that fellow, right? So, by 2 would be the component in that direction and by 2 would be the component in this direction. And so, that means it will be this into 1 by 2, this into 1 by 2. And so, I expect the answer to be lambda by this guy, basically this thing, into root 2, because it's going to basically be this component and that component will be equal. And so that tells you that this field must be root 2 times. So 2 pi epsilon naught r, well, that is into 2, and then there is a root 2, so or 1 by root 2. You expect this to be the answer. I haven't yet used that formula. But wait a minute, just think about this and that. It looks almost the same, and we can see why this must be true. So what I'm going to do is now show you that this line, the field here is the same as the field due to an arc. What arc? Arc of what angle? Arc of angle 90 degrees, because that's the idea, right? You replace, just join these two and replace it by an arc. So that this is a tangential arc. So basically this line becomes a tangent. So the answer for the arc is the same as the answer for the tangent, which is contained between the two. So that's exactly what, because you can see that this is 90 degrees, so this is the tangent. So if I draw this arc, the field of this arc, now this is 90 degrees, so you expect for the field of the arc, the angle to be 45, 45, pass exactly like that. And for the field of this arc, if I just substitute, I get lambda by 2 pi epsilon naught r into sine of 90 by 2, which is sine of 45. So you see the same answer. So you could have started off, instead of using this approach, we could have started off by saying that the answer for this is the same as the answer for the arc, and the answer for the arc will point right through the middle of this, which means 45, 45, right? And the field will be lambda by 2 pi epsilon naught r into sine of 90 by 2, sine of 45, which is this. So component of that, so that means this into cos 45. So this into 1 by root 2. So that is going to be the component in that direction. And the component in this direction happens to be the same because it's 45 degrees, right? Therefore, you can now conclude that if I had a full line, infinite line this way and that way, this component will be lambda by 2 pi epsilon naught r into 1 by 2. This guy's component like this will also be lambda by 2 pi epsilon naught r into 1 by 2. This is also lambda by 4 pi epsilon naught r. But this direction, for this fellow, the field will be upwards. And so that will be lambda by 4 pi epsilon naught r. This and this will cancel. These two will add. So that half will become double. And you will be left with lambda by 2 pi epsilon naught r. But that's something you already know, right? So the main point is obviously not to use this to prove those. Those are reasonably easy. Once you know this, you can use this in many, many situations. And that's what I'm going to show you now. So we will look at a couple of other situations where this is true. One more situation at least. Then I will prove why this is true. Let us now apply it to another situation. Okay. So here what I'm going to do is I have an infinite wire, a really long wire. I'm going to bend it like this and bring it there. So let us think of an infinite wire that actually goes like this. Now we could do many different things. I'm going to just join them. Okay, so I've just bent it like this, and I want the field someplace here, which is exactly, let us say, the same distance here as it is there. Okay, so I want the field there. Now by symmetry, you could argue that the field must be there, that way. How much is this field? That's the question. Okay, now let us think. Actually, it turns out that if I took this segment, you could think of the arc like this. You can replace this guy by the arc, and then I can replace this one by another arc. Actually, both of these have the same radius. And I told you that this distance is the same as that distance. We've chosen such a point. You can say, no, I want this point. Then, of course, you have to do a little bit more work. It won't look as neat, but let us just do it for this point to see the power of what we are doing. So this is an arc. Now what about this part? The answer is the same as this. And what about for this part? Well, this one keeps going forever like this. So this means I have to take it up to that point. Basically, this is the line, right? So the line that is going to join this at infinity is actually this line. Doesn't look like it's joining, but that's basically what it means. Two infinite lines basically are going to meet very far away. In fact, if it was here, it would have looked like this. If it was further away, it would have looked like that. You can see that it's starting to become parallel, right? And so that means this arc's extension, it would continue all the way till there. So finding the answer for this question is the same as finding the answer for this question. But this question, you already know the angle. How much is it? 90, 90, 90, 270. So therefore, the answer to this question is, first of all, it points in this direction, 45 degrees. That you know by geometry. Just look at this. This is going to be in that direction, right? Right in the middle. And what is the electric field? It is magnitude. It is lambda by 2 pi epsilon naught r into sine of this angle by 2. Now what is this angle? 270. 270 by 2, 135. So sine of 135 degrees. Now if you take sine of 135 degrees, it's sine of 180 minus 45, which is sine of 45, right? So this thing is just simply sine of 45, which is 1 by root 2. So what I'm going to do is, instead of rewriting this, I will just erase it and write it as 1 by root 2. But actually you can solve this in a different way. You can say, well, if I had a circle and it was uniform lambda, what would be the field at the center? 0. So the field due to this 3/4, if it was like that, and the field due to this 1/4 must be like this, that's how it cancels. But the field due to 1/4 you already know. It is lambda by 2 pi epsilon naught r into sine of 90 by 2, which is 1 by root 2, sine of 45, 1 by root 2. Except it's pointing like this. This is the field due to the quarter circle. This is the field due to the 3/4 circle. So basically this is the field due to the 3/4. You know that both of these are the same, and that's what we are getting here. because this is something that you've already seen. This is for the quarter circle, now you've seen it for the 3/4 circle. But what is interesting is not that quarter circle answer is the same as 3/4 circle. What is interesting is that if you took two wires, it behaves the same as a 3/4 circle. That's what is interesting here. Okay, and if in fact if I wanted the answer for this, if it was infinite and this was r and this was 45 degrees, that would be the answer for this piece. And if I wanted it only till this point, that means I didn't have this, the answer would be the same as for a semicircle. So what is interesting therefore, let me state that again here. So the answer for this at that point is the same as the answer for this at that point. Because for this infinite line, it would basically be this. And for this guy, what is the arc that you will get? You will get the same arc. So you can replace lines by arcs, and that is the power of this. Not just that, not only can you replace the lines by arcs, you have a nice formula for the arc. So you can, when you have a bunch of lines, for example, now if I had a square, and I wanted the field somewhere, let's say I wanted the field here, I would replace this by an arc. Okay, so I just simply take this and consider that. Or I just remember the formula for this, saying what it is. So I can just simply look at this angle and write the answer. Then if I wanted for this one, I take this one, I have this angle, I write the answer. And if I want this, then I do the same thing. I take the angle here and look at this answer. Of course, you'll have to do a little bit of, you have to do some cos theta, sin theta, you have to do some components and then finally find the answer. But it gives you the power of replacing an integration question by a nice simple formula. And anytime you can do that, it's very, very powerful. Trust me that when you look at formulas, you don't want to do integration. You just want to apply this by adding it up. Now, this doesn't work for all questions, but it works for many questions. Okay, so you see the power of the idea. You will see that as and when we solve many more problems that it's a really powerful idea. Now the question is, how do we prove it? How do I know it is correct? And that's what I'm going to show you now. Okay, so let us prove this.